In this video, we will discuss matrix vector multiplication. In doing so, we will start to see why matrices are relevant to systems of differential equations. So in linear algebra, one of the first things we would put on the board is a system of linear equations as follows. We can rewrite this as a vector equation, like so. And now that we have seen this, the method we use to multiply a matrix by a vector may seem slightly less weird. Linear algebra as a field was created to deal with equations like this, which we can rewrite like this, so it won't surprise us to see a sum that looks like this embedded in the definitions of linear algebra. We can multiply a matrix A by a vector V as long as the dimensions match. To match, these inner dimensions have to be equal. That is to say, the matrix has to have as many columns as the vector has rows. The resulting vector will have as many rows as A does. So think of the matrix A as a bunch of column vectors sitting next to each other. Then A times this vector is a linear combination of these column vectors with these vector elements as their weights. X1 times A1, X2 times A2 to X sub n times A n. it's this coefficient times this column plus this coefficient times this column plus this coefficient times that column. Which works out to be this. So this is perhaps not what you would come up with if you were asked to guess what matrix vector multiplication should look like. However, it does have expected properties. In particular, it distributes over addition. It can't be commutative because V times A isn't even defined, but we can move scalars around the way we would expect. Now, suppose we have a system of linear homogeneous differential equations. Like so. The similarities between this and what we've been looking at are obvious. In particular, we can rewrite this as a matrix times a vector. Thus, we can try to solve a system of differential equations by solving a single matrix equation. In this video, we have defined a matrix times a vector and seen how that definition relates to systems of linear equations. We then tied it back to the course to see how it relates to systems of differential equations.